Hello everyone, I'm Mr. Cobalt and welcome. In this video I'm going to be talking about VSEPR theory or VSEPR theory and five basic shapes that you can get from molecules using this theory. So the VSEPR theory stands for Valence Shell Electron Pair Repulsion. So I'll talk a little bit about what that is and how you can use that if you understand it to figure out what the shapes of your molecules are. And there are five basic shapes based on what are called electron group geometry, and I'll talk a little bit about that. But so VSEPR theory is valence shell. So we're talking about electron groups or electron pairs. So it says valence shell electron pair. So we're looking at the electron pair in the outermost shell of your atom. So those are called the valence electrons. And when you draw your Lewis dot structure, you'll see that you have these pairs of electrons around the central atom. And we saw this in, for your Lewis dot structures. And so in order to figure out the shape of your molecule, or the geometry of your molecule, you need to know how to draw the Lewis dot structures. If you don't do the correct Lewis dot structure, you're not going to get the shape right. So it comes down to Lewis dot structures. So you got to make sure that you do your Lewis dot structures correctly. And then the shape will be based on the number of electron groups in your around your central atom. So a couple of things I want to talk about is I mentioned already electron group geometry. So the electron group geometry is something I'll cover first, and then we'll talk about something called molecular geometry and how those two are different. So the basic shape is going to be based on the electron group geometry, which is the total number of electron groups. Now, we talk about electron groups rather than pairs. Pairs is kind of a misnomer in a way. We do look at pairs, but groups is a better idea to stick to, and I'll explain that in a moment. So we're looking at the total number of electron groups around your central atom. So those total number of groups include bonds, right? So the bonding groups and the lone pairs, the non-bonding groups. So both of those together equal the total number of electron groups around your central atom. So you're looking at bonds and lone pairs. And this is why we want to focus on the word groups and not on the word pairs. And the reason is because single, double, and triple bonds are treated as one group. So even though in your double and triple bonds you have more than one pair of electrons, because if you remember, each bond has a pair of electrons. There's two electrons in each bond being shared between the atoms of that bond. And so in a double bond, you have two pairs of electrons. So one pair for each bond. In a triple bond, you have three pairs. However, we don't count the double and triple bond as separate pairs of electrons. So when we look at our central atom and we look at the bonds that are bonded around the central atom, we treat double and triple bonds the same as we would treat single bonds, as one complete group. So a single bond is one group, a double bond is one group, not two groups. A triple bond is one group, not three groups, even though there's multiple pairs of electrons. This is why the VSEPR theory, valence shell electron pair repulsion, can be kind of misleading. So that's going to be the number of bonds and lone pairs. And when we're talking about lone pairs, this is going to get later, when we get into this a little bit deeper, when we talk about bond angles, we're going to have to look at lone pairs and multiple bonds to figure out what the bond angles are, because lone pairs and multiple bonds, like your double and triple bonds, are going to take up more space. They're going to need more space, and therefore they're going to have a larger angle. Okay, And this has to do with the R part of it, the repulsion. So repulsion comes from the fact that your electron groups around the central atom are all negative, right? Negative electrons. So because they all have the same charge, your different groups of electrons are not going to be one next to each other because like charges repel each other. That's why it's repulsion. So the idea behind VSEPR theory is that all of these electrons groups, these electron groups, either bonding or non-bonding, want to get as far away from each other as possible. So they're going to repel each other until they are equally satisfied, or where the potential energy has decreased to the minimum amount, right? And so that's how the electrons are, and the atoms are going to kind of separate and spread around the central atom in order to get as much space as possible. And that gives the shape or the geometry of the molecule. Okay, so I think that's a good introduction with the rest of this video and other parts of the video. I'm going to cover the different shapes. So the 5 basic shapes, I'm going to start with the electron group geometry where there are no lone pairs. So this is the geometry you get when, or the shape of the molecule is going to be the electron geometry. So I'll talk more about that later. So I just want to cover the basic shapes that you're going to be dealing with. All right, so, and this is going to be total number of groups. So we're not going to make a distinction between electron groups being bonding and non-bonding. So we're going to treat bonding groups and lone pairs as the same. So the total number of groups, if you have this number of groups, then you're going to have this electron group geometry. Okay. So what about if you have 2 electron groups? So I'm going to draw first generic molecules, and then I'll do some examples with actual molecules and Lewis dot structures. So when we have 2 electron groups, these electron groups are going to be around a central atom. So I'm going to be drawing this as like generic molecules, and I'm not going to have any lone pairs in my generic molecules. Lone pairs we'll talk about later. Okay, so let's say that I have B is my central atom, and then my outer atoms are A. If I have 2 electron groups, that means I'm going to have 2 bonded atoms. And so keeping in mind that the electron groups are bonding groups here, since we're dealing with atoms being bonded, those bonding groups of electrons want to be as far apart as possible. So the analogy I like to use is the analogy of if you're on the surface of the earth, so you have 2 people, right? You have 2 people, and here's your equator. You have the North Pole, South Pole. So here, and you have 2 people, and they are mortal enemies. They are one is the nemesis, the arch nemesis of the other, right? But they're pacifists, right? They're not going to go to war. They hate war, but they don't like each other. So what's the best thing you can do? Is you just stay away. So these mortal enemies want to be as far apart as possible. So what do? They move. They move away. So, but they can't leave the earth, right? They don't have a rocket ship. They can't blast off and get as far away as possible, but they have to stay on the globe. So in order to be as far apart as possible, where are they going to go? The farthest apart possible is opposite sides of the globe. So if I have one person here, right, and that other person wants to be as far away as possible, but the farthest distance, the farthest position away that you could be on the surface of the earth is to be on the opposite side. So there we have our mortal enemies. So if we represent the Earth as our central atom, so this would be our central atom B, and the 2 mortal enemies are representing our outer atoms. So we would have A over here, and A over here. And so the shape of this molecule, or what we call the electron group geometry, so I'm going to try to use that terminology throughout this video or the other videos. So for this group here, this is what we're going to call linear shape. So if I take this now and I draw a Lewis dot structure, right? So here's my beryllium chloride. So beryllium is my essential atom, so I have Be, and then I'm going to have chlorine on both sides. So I have a chlorine there and a chlorine here, like so. So I'm trying to figure out the shape, electron group geometry. What is the electron group geometry? Well, it's dependent on the total number of electron groups, bonding groups and non-bonding groups, or lone pairs. So here's my central atom. I'm only looking at the central atom. I don't care about what's on my outer atoms. I only care about the central atom. There might be multiple central atoms, and we'll cover that later. And we've seen Lewis dot structures where you have more than one central atom. In that case, you'll have to look at each central atom separately to figure out what the shape is around that particular central atom. So each central atom will have its own electron group geometry. So we only have one electron group, one central atom here. So we're looking at this central atom, beryllium. How many electron groups does it have? It has 2 electron groups. So whenever you have a molecule that has only 2 electron groups around its central atom, again, bonding and non-bonding, we're looking at total electron groups. Here we have 2 bonding, no non-bonding groups, no lone pairs. So here we have 2 electron groups, and so whenever you have a molecule where the central atom only has 2 electron groups total, the shape of that, the electron group geometry, I should say, is going to be linear. So this will be linear. So that's the first shape. So anytime you have 2 electron groups total, remember, bonding and non-bonding together, you're going to have a linear electron group geometry. Okay, that's the first shape. And the reason it's linear, again, is because of repulsion, the R. These electron groups, the electrons in this bond and the electrons in this bond, do not want to be next to each other. So because the repulsion of the negative charge is forcing them to be as far apart as possible. So that's why it's linear. Okay, what about the next one? So here we have 3 electron groups. So with 3 electron groups, same idea. Let's take my analogy. So I have my globe, right? I have my arch enemy here. I have my other arch enemy here. Now what happens if I throw in a third arch enemy, a third nemesis, if you will, right? So what's going to happen? Well, if I put another arch nemesis here, right? So now look at the angle between them. So the angle between them is going to be 90 degrees, right? But there's a lot of space down here. So these guys, remember, they're pacifists. They're not going to go to war. They're just going to want to move away from each other. So this 90 degrees here is too close. You got about 180 degrees of space here. So what are these two going to do? They're going to move away. So these two are going to move away from this guy. But then again, these two don't want to get too close to each other. So these guys are going to move down, right? Just enough where then they're going to be equidistant from each other. They're going to be equal angles. So they're going to be as far apart as possible. And in that case, you have a pie split into 3 places, 3 slices. So in the next video, I will continue. Thanks for joining me, and I'll see you in the next video. Thank you very much.